Hallo, wir suchen einen neuen Partner für den KI-Podcast. Bei Interesse einfach bei Robert oder Peter melden. Und jetzt viel Vergnügen beim Zuhören.
Hallo, liebe Zuhörerinnen und Zuhörer, das ist die Podcast-Folge 118 des Podcastes KI in der Industrie. Ich habe euch eine Kurz-KI-Folge mitgebracht mit dem Alexander Feldman von Xerox PARC aus dem Silicon Valley. Und wer der Alexander ist und was der macht und was der mit KI zu tun hat, das erklärt er euch jetzt am besten selber, denn er stellt sich erstmal vor.
Hey, I'm Alex Feldman. So I work in California in Palo Alto, and I work for Palo Alto Research Center. This is the research arm of Xerox. Xerox has several research arms. We're the biggest one, I believe, right now. So it's in sunny California. We're about like 200 people, 100 and something researchers. Many of us are working in AI. There are people working in physics. There are people working in mechanics. There are people working in all kind of things, like even biology, if you wish. So we do all kind of research for contracts, so to say. Sometimes the people we work for are internally from Xerox. Sometimes they're for government. Sometimes they're in military, and often they're in all kind of industry.
What topics are in the moment in the Silicon Valley when it comes to AI in industries?
Well, if I have to talk like outside of where I work, like Silicon Valley in general, you have the biggest players there who are Facebook and Google, and they also have their own industry in a way. I mean, it of course depends how you define industry. Where is
manufacturing industry?
Oh, manufacturing industry in this case. I mean, you know that actually some of the big AI companies, they also make their own data centers and electronics and all that. So the optimization of this process is important, and it saves a lot of money, and it's a big impact. So, for example, NVIDIA makes graphics cards, and it's a big player in AI, and they are like typical Silicon Valley. But nowadays it's globalization; they are spread all over the world, so it's not necessarily like Silicon Valley. So nowadays there is a lot of machine learning in industry. Sure. For all kind of applications, everything ranging from security to optimization of processes, and you can use like machine learning in many aspects. So and you can also, of course, use machine learning to make better the industry of machine learning much better. So making all those graphics cards, if you wish, faster and all that. So that's one thing. Another like relatively new, fashionable is not the right word, but is quantum computing in industry. So, and the connections between quantum computing and optimizations are deep. And, like quantum computers are not general computers. They optimize certain problems. How do you use quantum computers to optimize industry processes? And I mean, it's a big topic right now. So that's you have even companies like Amazon working on that.
In Germany or in Europe, we have a big discussion about selling models as a business model. We talked with Sepp Hochreiter from University of Linz, and he told us, yes, the new business model is to sell models like GPT-3 for industry, building GPT-3 models for industry. Do you think that this is a topic to building models, to use it faster, to use it easier?
Oh, definitely. The building models is actually huge. So that's we all know that, like when you do some tasks of AI in industry, you need the model, and I mean it doesn't matter if it's going to be manually built or learned from a lot of data, but it's an extremely costly process to train your model or to manually compose it out of components and all that. I don't think it's so easy just to have like a GPT-3 like universal model of the whole web, like you crawl all the text pages, all Wikipedia and stuff, and you try to build a speech model. So this is probably not going to work in industry, because industry everything is custom built, so there are multiple worlds. But you can, so probably it's a better, and there are many people at DX you talk with who can tell you about component libraries. So how you build models out of universal components that you connect together and you parameterize and you get the models. So trying to build component libraries, it's a big deal. It's going to help a lot. And there are people, I mean, actually in my lab, there are people working on component models for how things fail. So it's not typically you have like a component that, let's say, of a pump or something like that, which is how it like what's the flow, how it works normally. But when things start failing, you I don't know what you have, cavitation and fouling, all kind of industrial problems, stuff that, makes things break or people die or whatever in industry. People are trying to model for those, like all those subtle physical effects, and not only to diagnose, but also prognosticate in the future. You see what's going on. That's going to be a probably multi-billion thing.
What does it make difficult to buy models for components?
So first of all, the world is complex. Physics is difficult, and there are many things. So that's thanks God they fail rarely. So it's very difficult to create components with fault models which are physically correct. They represent the failing. So it's super expensive to. There are many people in Silicon Valley building test labs with tanks, heating tanks, and pumps and valves. And for example, I'm only talking about one industry, like let's say oil and gas, and Silicon Valley is serving the whole industrial world. So you build a test bed. It's very difficult to induce a fault. It's very difficult to think all the possible ways something can fail. How difficult it is to fail things. Mm-hmm. So this is very expensive. This is very costly, and there are many good people working on that. And I expect a lot in the future from there. And think about the environment. Now you have also Silicon Valley with Tesla, I believe, flying all around, and nobody knows how things work on the moon or Mars or whatever. We have very vague ideas. So how we're gonna make things fail in less gravity or like.
So, for example, you mentioned pumps. Do you think that the pumps manufacturer will build the models, or is it another software company who will build the models?
The perfect model builder is the one who makes the device. Mm-hmm. So because in order actually to make something, you need your blueprints, your draft, and then this corresponds somewhat to a model. Of course, it's incomplete. Again, the biggest challenge is to make the model complete and cover all situations and predictive in all situations. And that's where actually our AI methods fail. When you don't think of something and then it happens, and then your prediction models fail. And then you have in the diagnostic community, you have a false positive or false negative. You have to do it again. So
we need to invent new AI methods?
We have to improve existing AI methods. We have to combine. The way I see it, going from conference to conference, is that most of the challenges are covered. But the thing is that different specialists, they have different algorithms, different modeling approaches, and they only solve one challenge at a time. So we're still lacking a comprehensive framework that solves the whole industrial life cycle, if you wish, something from how the device is made to how it's used. And for example, I'm a big fan of sustainability, and AI is big there. Very often we don't think about end of life of, when you make something in your industrial world, how do you dispose of it, how you demolish it, how do you clean after that, and all this kind of stuff. So that's AI can help here.
Mm-hmm. So do you need to invent new algorithms specialized on new models, on industrial models?
Personally, yes. Depending on our customer, we have every now and then we look at different subsystems, let's say like heating stuff or like refrigeration but again, sometimes, in this AI business and computer science is very good in abstraction. Sometimes you have to talk meta and meta and meta. So we are talking about industry, but what about the industry of building industrial machines? So that's, you may start designing a quantum device, optimizing something for industry, and you may need some diagnostics of the device itself. So that's, it happens to us. And then you may have cryogenic systems and refrigeration there, and the algorithms and the models would be somewhat similar to the ones you use in buildings and or industrial coolers or something like that. So this happens all the time.
You mentioned that the big players are working on pumps and building models for pumps, but they don't have the domain knowledge. Is it a problem?
Yes, it is a problem, but also they can hire and they cooperate, with universities, they have test labs, the big players, they can easily talk to the producers of those things. Although sometimes, the producers are focused on actually building more and better and selling more. So sometimes it's difficult to find the right places in a, say, pump manufacturer or valve manufacturer to talk with. And also keep in mind that there is also the cultural thing. So if you are making some devices, it's relatively difficult to start talking about how your devices fail. You're going to tell me my devices never fail.
So what is your actually topic you are working on in the moment?
Right now, I have two things. One is I'm actually working on effects of cavitation in pumps right now. So that's we have a test bed. We're trying to induce some cavitation effects in valves and pumps. And my job is to use signal processing and advanced algorithmics to have better prognostic methods that can more accurately predict when the cavitation effect will make the pump stop delivering the desired flow or whatever you are optimizing there. And we're using multiple types of measurements, multiple sensors and whatnot. And I also have work on security. Security and diagnostics and failing, they are of course related. Only in one case it's deliberate, like the other. In the other case it's an act of nature when something fails. So I'm looking for parallels and algorithms and models that can be used in both, and approaches that can be used in both failures and security attacks. So that's...
Let's stay with the pumps you're working on. Can you describe the process and what you are doing?
Sure. So we have a lab, and I work with wonderful people who know about actually building those pumps and connecting them, and then they also provide measurements. So the first thing is always you collect the data.
Sure.
And out of
a lot of data.
We do. I mean, so we're quite proud, So that's it's super expensive. We're talking about tens of people working years to collect data. So it's a big investment from our bosses. Once you collect this data, you have to identify the best method to work with that. I mean, one of the what I dislike this metaphor, lowest hanging fruit is start training something, some CNN or whatever is the fashionable abstraction of the day, like. And then you start classifying, nominal versus some, I don't know, cavitation or leakage or whatever you're trying to track. Then you're looking for something more powerful, something that you can apply to other systems and so on. So you start, for example, trying to build like a physics-based model. So you take your favorite environment, Python or MATLAB or Mathematica, and you start looking for flow models, and you figure out, you take all your system, not only the pump, you have something else like pipes and valves and heaters and whatnot. And you have some medium water or whatever is in the pipes, and then you start writing down those equations and plotting and seeing if this is what you measured. You have a lot of data to start with, so it's easy to compare. And then you keep doing that until you end up with a good model. Then you have to, typically in diagnostics, you have to do some kind of, in prognostics, some kind of parameter tracking. And then there are the standard methods, and they all can be improved. I mean, for example, you remember this from school. If you have to track a system, you always throw like a Kalman filter first. But then Kalman filters, you need a linear model, and those effects of how things fail, especially in pumps, are very non-linear. So then the Kalman filter is not going to work there. It's going to give you a lot of error. So that's then you try something else, a scented filter or particle filter. But particle filters don't scale. You need gazillions of particles and all that. So then you have to start about other methods. So that's you can do some model-based, residual-based approach, but then the model becomes difficult because you have to, so to say, to split the model into sub-parts. So the whole thing is manageable. But how the mathematical formal split is different. How the physics is split. You cannot only take the pump without the inlet and the outlet and the whole thing, for example. So that's quite challenging, and it's a difficult process, but it's kind of interesting. So you keep doing that.
You mentioned neural networks. We have a good old-fashioned AI, random forest, and neural networks. How difficult, in Germany there's a discussion, it's very difficult to combine both, the good old-fashioned AI and neural network. What is your opinion? Is it so complicated to combine both technologies? It is.
It is difficult, and actually in AI, everything is difficult to combine. There's so many interesting algorithms. It's one of the biggest challenge how to make everything work together. Actually, I want to give you a better example of what's more difficult to combine. If you take the business, of discrete event systems, something in programmable logic controllers, you have it all over industry. You have thousands of them everywhere. So they're perfectly this is the very old thing, you model them as state machines. But then behind the PLC, what the PLC controls, it's easier to model this as some kind of differential equations or circuits, if you wish, or some combinatorics and all that. And how do you connect, the state machines with all these equations? People have tried to do that. There are all kind of formalisms which are more advanced, hybrid methods and whatnot. But then all kind of weird things start happening with the numbers and the variables, because classical mathematics likes all these smooth words with derivatives and everything, and then you have all those discrete methods where you switch from 0 to 1 and all that, and then weird things happen like at the boundaries when you start switching, small numbers, computers, they run out of precision and so on, and you have to look very carefully how you combine them, and this is where all the research goes, and that's why you have conferences like this one, and then people talk about how they solve particular problem. I haven't seen a universal solution. Mm-hmm. The kind of the same reasoning applies to neural nets and random forests. Like random forests, it's all about like splitting variables and jumping here and there. And a neural net is a very elegant, smooth thing. You have your sigmoids and your summations and floating point numbers and the great computer science problems that you can never say if x is the floating point, if something is equal to 0. You have to check if it's like x minus epsilon is smaller, absolute value is smaller than something. So that's because with the floating point numbers things, so what's going to happen is that you're not going to converge, you're going to run into numerical problems, you're going to get stuck in optima, all kind of weird things are going to happen to your model, so you're going to get garbage out of your prediction and you have to start it again. So that's...
At the end, I want to ask you talked about quantum computing, and this will change the whole thing, AI, machine learning, totally, because we do need more new algorithms, we need new processes for doing it. Are you working on it, and what is the future of this?
Yes, so if quantum computing works, we don't know. I mean, probably nobody knows, and I believe so that it's going to work one day. First of all, AI, both in industry and outside, in other areas, is actually applied optimization to real-world problems. So most algorithms are trying to optimize something. Even decision-making can be thought of as a type of optimization. You can use optimization for decision-making in the other way around. Quantum computing is going to be the universal optimizer. So imagine what if you can optimize all your processes, logistics, manufacturing. Imagine that you're able to answer what's the theoretical optimization maximum of how fast computers can be manufactured, or how much energy, like in industry, super important aspect. What is the most efficient from the energy standpoint process of making something? So that's maybe we're going to discover some so cheap sources of energy that we're going to solve the problems, of pollution or whatever.
Where do you see the most impressive research when you're looking around the world?
Oh, it's everywhere. It's happening a lot of good work. I'm super glad that people and industry and companies are spending that. So it's when it comes to AI, I mean, you cannot miss all the autopilots and space and autonomy. And I believe in a better future. It's also in industry where the dirtiest and the most dangerous jobs will be performed by robots. So this is amazing. People will be creative and inventing, solutions to problems that are dangerous, like how to make things nice and fast and safe, and so that's quite awesome. And there are also many things outside of industry, people are answering mathematics and physics and space and biology and medicine is improving a lot, and there is also industry for medical appliances, and it's kind of actually the most rewarding thing is when you can apply something from pumps to industry. For example, I didn't know before I started working that cavitation in pumps, which from industry is a very dangerous effect, you can use it for cleaning in medicine. And I also didn't know that you can use it in some micro, I still don't know details and I'm very interested to read. You can use it for cancer therapy, drug delivery, in tissues and all that. So maybe one day we'll be using diagnostic methods control methods from industry also to help medicine and the other way around. So that's going to be quite awesome.
So you're now based in the Silicon Valley. You have a lot of connections to Europe. What about China? Is it a black box, what they are doing, what they are researching on?
Unfortunately, I don't have many friends I haven't been a lot to China at universities. I mean, they're growing great, and I'm somewhat concerned about how they're using AI, for example, by state for tracking people or something like that. So there is it's super important, like ethics in AI, and in industry is double important when things are dangerous. So the answer is I don't know about China and US and Europe. I mean, I'm from Europe. I was born in Bulgaria and I studied in the Netherlands. So Europe and the US, we exchange a lot of knowledge. We're natural partners in this business of developing research, technology, science, whatever. China is the newcomer to the club, when we're exchanging ideas and everything. And we're very excited to work with. I mean, it's great potential and wonderful young people working on many things there. And we're yet to see how the whole long-term cooperation process is going to go. So that's we have to watch.
In Europe, we have a big discussion about ethics in AI. Do you have in Silicon Valley the same discussion about ethics in AI? Because in Germany or in Europe, we think, we are doing borders and we are doing regulation, and this is not good. But in my opinion, I think there's a mind change also in Silicon Valley to do more ethics and to more regulation on AI.
There is, of course, the contradiction. Many companies in AI, you want both to preserve privacy and freedoms and not track people and all that. But then there are many products that would benefit from this type of tracking and invasion of privacy. But I would say that in particular, California, which is somewhat different from the rest of the United States, is very interested in ethics and privacy, and there is a lot of work. I would say up to par with the Northern Europe standards in privacy protection, GDPR, and all that. So we have our own Californian equivalents of that. I'm not exactly from this field, so it's difficult for me to judge the details and the subtleties, but I think it's comparable to, and it's the best in the world.
In Germany or in Europe, there's a discussion that GDPR is a border, it's a break for AI. Do you think this is a break?
In a pure technological way, yes, it puts some limitations of what you can do. How much data you can collect and all this. So in the technical sense, yes, but then keep in mind that AI is supposed to be designed to serve people in the way we want, and we share all those, especially between the States and Europe, those common values. We want to, multiple generations to create a nice technology and to solve the problems of the planet and everything to be fine. So you cannot have an AI system which kind of interferes with those values. So AI is in a way a model of the world, so of the whole world, and we should also model the values there and all that. So GDPR should be inside the AI model.
Thank you very much.
Thanks.